to start with the bedding, like I said, today's class is going to be short and quick one. Yes, you have already explained all the parameters using that single figure. So these ones are just reading. So the key thing here is that you know what a berm is and what a burden is, what spacing is. And I took my time to explain to make everything clear. So these are just reading. So burden is defined as the shortest distance to relief at time of blast. So when we are blasting, what this one is saying is that when we are blasting into the burden. We didn't blast into the spacing. So that's why I said the burden is always with respect to the free face. The free face is where we are blasting into. Okay. So the burden is the distance to relief. Okay, the distance to relief because we are blasting to the free face. So the distance to relief for the holes at the back to blast into is the bedding. All right. If the bedding is too small, rock is thrown at a considerable distance from the face. Yes, that one is true. If you have too small bedding, the rock will be thrown at a very large distance. And if the bedding is also too much, it can cause over confinement of the blast holes, which result in higher levels of PPV, air blast, and those stuffs. In practice, this bedding should be one half or 1/3 of the bench height. Okay. So if you are designing your bench, the pattern, the drill pattern, the bedding that you use to be at least should be one half or 1/3 of the bench height. So if your bench height is 8 meters, half of your bench height or 1/3 of the bench height should be your bedding. Okay. Then talk about the spacing to, we know that already, the distance between adjacent blast holes measured perpendicular to the bedding. The distance between the blast holes in the same row, and the spacing is dependent on the bedding. Okay. So the spacing should be 1 to 1/2 of the bedding. We have the stemming distance. So do you know stemming already? Stemming. If you don't know stemming, let me go back. Guys, okay, I didn't talk about it. So stemming is, you know that after drilling, we do priming. So let me start with priming. Priming is when we use the booster. So you connect your booster to your detonating cord, okay? The booster like detonating cord. So when you are doing that, you call it you are priming. So in some mines, the detonating cord, they call it downline. Downline. So when you connect your booster with your detonating cord, that is priming. So after priming, you do what? You charge the hole. So after priming, that's where if you are using ANFO, ammonium nitrate fuel oil, you pour it in the hole. If you are using emulsion, you pump it in the hole. Okay. So the stemming, if the hole depth is, let me see, 9.5. The hole depth is 9.5 meters. Okay. The stemming should be fixed. So you can say use 3.5 meters for stemming and the 6 meters for the charging. Okay. So you pump like, let me say, 150 kilo of explosive into the hole. You pump that explosive and the explosive into the hole, then it will fill the 6 meter. Okay. Explosive will fill the 6 meter. And the remaining 3 meters on the surface. So let's say this is too much. Okay. Let me say we are using 7 meters for explosive. Okay. So the pink one you are seeing is the charged column. Is it violet? Yes, the violet color is the charge column. That means you have pumped explosive into it. Okay. So let's say this is 7 meters. Okay. 7 meters column pumped with explosive. Then the remaining 2.5 meters will be your stamen. Stamen is where we use inert material. So we will use it to uh, some force to compress the explosive. Okay, to compress the explosive, right? So some of the materials we use for stamen, you can use draw cuttings, and also um, chickens, chickens. Use them for the stamen. So we break them to smaller pieces, then we use them to stem to in some another way to compress the explosive, okay, to compress it. So assuming after charging the hole and you don't stem it, what do you think will happen? When you blast this particular hole, you end up uh, getting all the energy being released out of the hole, right? If you don't stem it, you don't use any material here to compress it and you blast the hole, all the energy will come up. Then instead of them breaking the rock, the energy will come up, right? And it will be wasted to sound energy, air blast, and so forth, right? So that's why we stem. That's why we have to stem. And also we have something we call the air deck. So air decking. So that was you divide it and okay, let me use this one. So if you charge, you pump explosive to fill this section, you leave some air deck, then you stem this part. So here will be the void. You leave some air deck. You use something you call the gas bag. The gas bag. You pumping, you mount the gas bag there so that it will leave a gap between the charge column and the stem column. Okay. So here will be air. So that's what we call air decking. So this air decking is just to help in the explosive energy distribution. Okay. It will help in explosive energy distribution. That's where sometimes we need air deck. Okay, so now we know what stemming is. We know air decking. We can proceed with the rest of them. Uh, Stemming distance to be 0.721, the bedding. But this glass is poorly designed. The above stemming distance is not adequate. A delicate balance between okay, yes, I made mention of this. Fly rock and excessive air blast can be caused when there is not enough stem. And if you don't stem it, you'll get fly rock because some of the energy that we're supposed to go into the formation and blast the formation will be um, to come out, okay, to come out of the hole. It will be wasted as fly rock and sound and air blast sort of. We have spoken about the stemming materials already, so you can proceed with that. Subgrade drilling, that's the subdraw that I was talking about. So the subgrade tool we are saying is approximately 0.3 of the bedding. Okay, 0.3 the bedding that you use. That is the subdraw or the subgrade. Incline hole drilling. So let's look at some of the advantages of incline hole drilling. Let's back break. Do you know back break? Okay, back break is simply breakages beyond the desired excavation limits. Let me come back to my favorite picture. So if this is the bench that you are blasting in, and in blasting, it is assumed that uh, each hole that you blast, the blast will cover half of the bedding. It will blast half of the bedding. Okay, so you realize that at the end, if you want to blast this particular bench, after blasting, you realize that there will be some breakages beyond where you wanted to blast. So those breakages are what we call back break. Okay, back break. Because you want to blast this portion of the bench. But after blasting, you realize that there are some breakages beyond the boundary that you wanted to blast. So those breakages are called back break. Okay. Back break. Yeah. Less problem at gate, the bench stability is better. More true, especially on low benches. We have better fragmentation. So if you want better fragmentation, you have to reduce your parting size. Okay. If for instance, you are blasting the bench that you are blasting, if the bench that you are blasting has all inside, because it has all inside, you have to make sure your parting size is in such a way that you will get good fragmentation. Because at the end we have all, so you have to recover it. But if you increase your parting size, that is, you widen your parting size, you're bearing in the spacing, you end up getting poor fragmentation and even boulders. You don't want that to happen at where we have all. If it is waste, so in mining, you realize that we have different parting size. We have parting size for all, and we have parting size for waste. We'll talk about all of them when we are using the software, so don't worry about that. We'll start with the software so that you know what I'm talking about. You realize that and you appreciate that we have pattern size for all, we have pattern size for waste, because for the all, we want good fragmentation. So you also realize that the pattern size for the all is the burden, the spacing are smaller as compared to that of the waste. Because for waste, it is waste. There's no order, so um, we don't show much concern as compared to all. Um, Selection of blast hole size. Okay, the blast hole size. When we know the blast hole size dependent on the drill bit, the diameter of the bit. So that one, depends on the drilling economics. Okay, the effect, effect of fragmentation on air blast, fly rock, and ground vibration. You have to consider all of them, but we know if your road, the diameter is wide and you are pumping such diameter. Okay, let me ask you, if you have, um, if you are using two type of bits, okay, 165 millimeters and 115 millimeters bits, okay, that means the diameter of this hole will be wider than this one, right? Because 165 is wider than, oh, what have I drawn? Okay. You know, 165 is wider than 115. So if this is 165, let's say this one will be 115. With these two diameters, okay, which one do you take will accommodate more explosives when you are pumping explosive into? Which of them do you think will accommodate more explosives?
The 165.
165.
Yes, because it
165.
is, yeah, because it's wider, so more explosives will go into that particular hole. Yeah, so we consider all of them. We call something the stiffness ratio. The stiffness ratio is simply the ratio of the bench height to the burden. Okay, the bench height to the burden.